Many thanks for the introduction. So I'm grateful to the Academy for electing me as a fellow. So it's a great honor. So this is the talk I'm going to give today. So origin of asymmetry uh, uh, and the friction in multiscale systems. So it's a physics talk. It has some connection with turbulence. So but it's slightly change in theme. So let's start with a movie clip. This movie, I guess, a lot of you might have seen. So uh, I'll play this.
So what next?
Okay.
With a single equation, that time had a beginning. Wouldn't that be nice, Professor? So one simple, elegant equation explain everything.
Yes. It would indeed.
Thank you.
Okay, so this movie clip. So I will go to the next slide. So this movie clip, you see that there is a dream of physics to explain a lot of phenomena using a single equation, and I come from a different perspective. I believe that's not quite possible because the world is very multi-scale, very inhomogeneous, a lot of different kind of phenomena, and so that is what I will highlight today. So it's a multi-scale nature leads to various phenomena which is not quite explainable from very fundamental perspective. So this is a one paper which is very prominent is called More is Different by Anderson. That is in, I mean, my talk is in that theme. And I also wrote a paper on microscopic versus macroscopic on the similar theme. There's some more works which I will tell a bit later. So basically there are symmetries play a major role in modern physics. And so for example, symmetry under space translation. So laws of physics are same here in Kanpur and in Bangalore. That symmetry leads to conservation of linear momentum. So there are three fundamental symmetries which are listed here: spatial translation, spatial rotation, and time translation, and they are exact symmetries. They are not violated. But there are some other symmetries which are not exact. For example, mirror symmetry. That is the law same for left-handed system and right-handed system? I will briefly tell this at the end of the talk, but I will more focus on time reversal symmetry. So I will explain what is time reversal symmetry in coming slides. So essentially, is there a way to say the time going forward and time going backward? What is the difference between the two scenarios? So since some people may not be aware of this the symmetry, I will give some simple examples to illustrate what does it mean by time reversal symmetry. So time reversal symmetry is respected by three fundamental forces: gravity, electromagnetism, and strong nuclear. But weak nuclear breaks the time reversal symmetry. These from the fundamental perspective. So if you look at this, like gravity, things particle falling down, or I push the particle up with the velocity reversed, it will go to the same height from where it fell. So that is respecting time reversal symmetry. Okay, I will be more explicit by an example. So I'll give several examples. So weak nuclear disrespect to symmetry, but as I said, I will not follow the idea of coming from fundamental laws, but I will go more for macroscopic phenomena or more of a general big phenomena. So what is the basic controversy? So if you look at Newton's laws, mass times acceleration is force. So if in this equation, if t goes to minus t, since it is a double derivative of r with t, so it turns out that this term r double dot does not change sign. And if the force also does not change sign, as I said, for gravity, for electrodynamics, strong forces, force is unchanged with t goes into minus t, then forward motion and backward motions are symmetric. Okay, so what does it mean? So if I send a projectile from position A it will go to position B, right? It just goes the parabola. Now, if a time reverse it, that means it goes from B to A, right? Time reverse, I just change the velocity at point B and it's just going to go back. Now, this backward motion. Now, is the backward motion realizable in real system? Now, indeed, if I shoot a particle from B and it will go back to A, that means the time reversed trajectory is realizable in real life. In fact, that will be identical to the what we can do by shooting a projectile from B to A. Okay, so this is what time reversed trajectory is very much obtainable by just in real example. Now, another simpler example is that if a pendulum is swinging, so it goes from left to right. Now it is a forward motion. Now, of course, from it reaches to the right, it comes back to left. But that is time reverse motion of the motion of the forward motion, right? So when it comes from right to left, that is same as time reverse motion of the forward motion. So both these motions are equally likely for pendulum. Of course, frictionless pendulum. If it is friction, then there will be a problem. But we assume frictionless pendulum, and then these two motions are equally likely, and forward motion and reverse motions are the same. Now, in real systems, do we see this kind of going forward and going backward being equally probable, or system going forward or backward in both ways? Now, let's look at examples. We find in real life time moves one way, like we are born, live, then die. It doesn't go backward. Seminar will not go backward. I mean, this can't happen. This doesn't happen. So how does this asymmetry arise? That is a big question. Now, one way is to try to derive it from fundamental laws. We'll try to do from weak nuclear and try that. But another way is to do from some macroscopic principles. So second law of thermodynamics is often, so which everybody knows that entropy increases. Entropy, if I keep a gas particles in the left, it will basically diffuse. That's what is going to happen. Now, so I will not discuss that. This is second law of thermodynamics, which is invoked to explain time reverse asymmetry. So it's from gas scattered everywhere. It doesn't go back to one part of the room. So that is asymmetry, which is coming here. Now let's revisit for the aging process. Now, from child we grow to adult. Now, what is meant by time reversal? Now, I think of it, in fact, to me, it is not a puzzle at all. Now, if I want to go back to a child, so what do I need to do? I need to reverse all the molecules in my body, as well as all the air coming to my me, okay? Reverse it. So it turns out that I need to breathe carbon dioxide and breathe out oxygen. So in fact, this is not possible at all. So this is, in fact, is very ambiguous question that why don't we age? We age because it's a very complex connected process. We breathe oxygen from the atmosphere, we are interacting, there's a big set of molecules in my body. So aging is natural. I mean, we really don't need to invoke the fundamental laws for explaining aging. Now, so aging is not really like pendulum swinging back and forth, or many systems interacting with each other in reversible manner. This is not reversible. Of course, there's a lot of friction involved, which I will say, like I eat food, and there's a dissipation of energy of what I intake. So this is basically not a problem if you think in a very macroscopic way, and that's why some things are made more mysterious than what they are. That is my take. I mean, if you just think of multiscale process. Now, there are more ways to break the symmetry. We don't need, well, it's great to have fundamental laws break the symmetry, but for real life, we explain that by breaking nonlinearity, forcing. So there's forcing in all systems. Like pendulum, if you force it, then it breaks the symmetry. It is not same forward and backward. Force means apply external force on that. Structures and friction. So these are 4 macroscopic ways where we can break the symmetry of time reversal, time going forward and backward. Now, the example is in chaos, we say that it's the 3-body problem. two stars and one planet, and it's very easy to explain that this motion which is going forward is not going to come back in this system. It's not going to become going back and forth. There is a theorem that it will take infinite time to go back, or very large time, but irrespective, here going forward and backward like pendulum does not happen in nonlinear systems. Similarly, now just imagine we thought a projectile, no? So projectile was going from left to right and right to left. But who shoots a particle? We don't shoot a particle. We shoot a cannon. Now, cannon coming from a tank is going to go down like this. Now, what is the probability that when you shoot it backward with precise velocity, it's just going to go back in? Is, I mean, this very small likelihood. So structure also break symmetry. So I think very idealized way to look at a problem is not going to explain the real life scenario. If I put a rocket, then definitely it's not going to come back. So life is not like pendulum swinging in back and forth. That's what I wanted to say. Now let's look at, so these are some simple ways to look at time reversal symmetry. Also friction. So from A to B, the ball itself is going like that. But if I put friction, then it's going to go to B prime, not to B. Now B prime, if I go back, then I go to A prime, not go to A. Because friction is decreasing the range of the motion. Now, I'm just going to go to turbulence now to make it slightly more technical. Of course, they say, well, everything is so trivial, then what are you talking about? This is all child's play. So let's look at it more complex system. So let's take turbulence example where all these things happen: nonlinearity, forcing, structures, all of it is there in the system. So in turbulence, typically we have a large forcing at large scale, and that goes down to that goes down to small scale and down like that, and finally it goes into dissipation. So that's where friction is. Now, so there are a lot of theories, but one important theory is by Kolmogorov, according to which this is the law. Okay, so this velocity field, if I take a snapshot and I change the velocity field to u to minus u and take a cube, okay, then I get this 4/5. So this is called energy cascade rate by u. So that is energy flowing from large scale to small scale. Now this is a law. Now what if I do time reversal? So time reversal means u goes to minus u. Okay, so this left hand side will change sign. That means this minus will become plus, right? Because pi u is positive. So what does it mean? It means the time reverse system energy will flow from small scale to large scale. That means my coffee will basically not mix, but it's going to unmix in a time reverse system. Now that is not possible. Okay, so and why it is not possible? Because there is a friction in the system. So it turns out in turbulence there is a natural direction of time, which is from ordered structure to disordered structure, and that is easily explainable by many ways. I've told you one way. Other way is to say the friction is there, so that sets a cascade downward. Now energy flows from large scale to small scale, but in the reverse process it will happen other way around. So we can basically, in fact, it's a very interesting system which I can't explain due to lack of time. So time reversed, we can rule out by just seeing a snapshot that this is time reversed or forward in time. Okay, so this appeared in Europhysics B journal. So nice problem solved, but there is a catch. Now it all looks like I can explain by friction, but now in theoretical physics, the problem is friction. So friction is kind of not a very, it's not a fundamental force. So people don't like it. So friction, in fact, if you look at a lot of books on classical mechanics, there's a friction, don't talk about it. I mean, we want Hamiltonian system, energy conserving system, and friction is not fundamental. But I believe dissipation is fundamental. And in what way? Now let's look at turbulence itself. So we have a lot of fluid particles. Okay. Now if you just see from fluid particle perspective, the total kinetic energy is conserved, right? In fluid, all these particles are going around. hitting each other, and this assuming elastic collision, the energy is conserved. Now, what does turbulence do? What does turbulence do is takes the coherent kinetic energy, which is the blue large vortex structures, and that pushes into thermal energy. So in turbulence, energy is going from coherent to incoherent. So total kinetic energy is conserved overall, if I look at molecular perspective, but the molecules are also arranged in a nice way in a turbulent flow. And of course, there is some jiggly motion at very small scales, that is incoherent motion. So in the full system, there are fluid energy, which is coherent energy, we call it U squared, and there are incoherent energy, which is macroscopic motion. So to me, friction is natural, and it's just conversion from coherent to incoherent. So and it turns out that we can apply this logic to from multiscale perspective. We should not just seeing particle colliding basically in a single scale, collision scale, but we can look at it from multiscale perspective. And earthquakes, cracks, so there is a lot of dissipation in this system. Even in quantum systems, there is a dissipation. So this is called quantum dissipation. It's important, but I believe, hopefully, okay, I can't say I believe, it's a good idea that we can say that let's think of some coherent energy like in superfluid, macroscopic wave function, and then some of it gets dissipated at small scales, which is invoked by the way in superfluid turbulence, but I think it needs more explanation. In human body, there is a nice way to explain arrow of time or energy dissipation. Food intake, I take energy, and that food is macroscopic, is going into energy in the cells. So basically, there's a cascade of energy from food to cell level. Now, all this is great, but it turns out there are some anomalies, or there's not. So I'll just take 1 minute.
You have 3 minutes. You have 3 minutes.
Yeah. So I'll just take one or so in 2D turbulence, energy flows other way around, but it turns out the Kolmogorov law is modified. So I will not detail this, but it turns out the arrow of time for this is in such a is like energy going from small scale to large scale. But I'll skip this part. So cosmological arrow of time is another issue which is connected. So we can form structures by turbulence, and so I think I will skip this part. I will, but what I want to say is that in some systems, forward motion of time is for making structures. Like in 2D turbulence, like cyclones are formed because of 2D nature, or in gravitating systems, is the natural way is to get to formation of structures, and that's not like more entropy. So entropy increase by macroscopic system, there are some issues involved with that. Now mirror symmetry, I'll just say that. So in IIT these Amalthas trees are found everywhere in IIT Kanpur. Now we see this twist. You can look at this thing. I took a picture of this, not a great picture. So this mirror symmetry is broken here. Now, would you like to explain from weak interaction? No, this is by differential drying. So there is a drying of this leaves. It's not leaf actually. It's like a fruit in some sense, and that differential drying is leading to mirror symmetry breaking. So environment plus system properties of moisture is absorbed more in one side than the other side, can lead to breaking of mirror symmetry. So conclusion, multiscale description helps understand breaking of time reversal as well as mirror symmetry. So we invoke friction, forcing, nonlinearity, and this is a universal framework. In some sense, you can put this together in one framework. And so also origin of dissipation. I think I'm more quite keen on this dissipation mechanism, which could also be applied to complex systems like quantum dissipation. Okay, so I think I will close here, and I'm happy to take questions. So some papers are here if somebody is interested.